Good Thursday to you, everybody in Gov 603. Welcome again to week 11 and our review of week 10. How's everybody doing? Okay, you doing well? Let's get this started off correctly. Little a little tea for this morning because I am sufficiently caffeinated. Been up for a while and had my espresso. Okay, let's take a look at week 10 because this is particularly important this week. This is our first week of, actually sort of hands-on the empirical process. And in this case, we're looking at quantitative methodology. And in this case, we are looking at simple regression. Okay, this is important for you to remember because you will see it again on the exam. And that notwithstanding, regression is an extremely useful tool by way of a research methodology. And you can use this calculator online for future research purposes, okay? Because what linear regression does, it's a mathematical formula that calculates two things primarily. I mean, there's a bunch of other stuff with, there are a whole bunch of calculators out there, software suites that you can use for linear regression. Probably the industry standard, I'm going to get back to what it's for in just a second. Industry standard is a software called SPSS, like Sam, Papa, Sam. And if you ever come across SPSS, it's used for quantitative research. Okay. So there are a number of values that can be produced during a regression analysis, but the two that can prove useful to you as a researcher are the R and the R squared values. And we're going to talk about that, and you need to understand what they mean. And if you see it, on an exam, you'll be able to explain it or even work a calculation very quickly. And I would include a calculator for you if such a thing occurred. Okay. But it's a really, really useful empirical research tool. All right. So let's take a look at it and make sure that everybody is on the same page. Okay. So from week 10, question number 1, using Google, what does a linear regression's R and R squared value signify? Include a link to the source that you use to answer this question. Okay. So when you run a linear regression, you don't have to generate a chart, a scatter plot or otherwise. In this case, I wanted you to, because I wanted you to be able to see information data graphed on types of graphs that I've been asking you to be able to identify. All right. So when you run it through this calculator, what in the world do those two values mean, R and R squared? Let's see. Let's go to Ashley for this. Regression measures how one variable affects another, and the R and R squared values are an important component. And you, Ashley, you refer to statology.org. Explains that the R value is used to signify the correlation between the two variables. Okay, so let's pause on that one first. The R value signals the correlation. What does that mean? That means that the R value tells you that, and the numbers that you get are decimal numbers, but they're expressions of percentage. So whenever you get an R value in your head, or you can do it on paper, times by 100 to move that decimal place, over to the right. Okay. And so what it's telling you is this is the percentage of the time that when this thing is happening, this other thing is happening. Remember, that's correlation. But correlation is not causation. Now, correlation and causation often go hand in hand. It's like, duh, when it's dark and cloudy overhead, and then there are drops of water falling from the sky, there's a correlation that when it tends to be dark and cloudy, it tends to have drops of water falling from the sky. Well, as it turns out, the drops of water are being caused by the moisture in the clouds. Okay, so that's causation, but not always the case. It could be dark and cloudy, and there could be no drops of water falling from the sky, or there could be drops of water falling on you that aren't coming from clouds. Like maybe an airplane overhead decided to, dump its, how can I put this, waste tank. Sometimes in an emergency, especially if they're going to have to make an emergency landing, airplanes, not often, I mean, very infrequently. So, I don't want you to run around going like this, but airliners will dump all the additional weight, including fuel and wastewater. Out it will go. And so, suddenly it rains down on you and you're like, oh, hey, where does that come from? So it's not always that when things are happening at the same time, the one is causing the other. But the R value tells you the percentage of time that this is going on, that is also going on. All right. It's expressed in a percentage. All right. So it's the correlation between the two variables, the predictor variable and the response variable, or, these sometimes get different names. Predictor is sometimes called independent, response is called dependent variable. Okay. The R squared value, back to Ashley again, the R squared value is then used to signify the portion or proportion, excuse me, my mistake, not yours, Ashley, of variance occurring in the response variable as a result of the predictor variable. In other words, R squared is an expression of causation. Remember that. R is an expression of correlation. R squared is an expression, a statement, whatever word you like, of causation. And this too is given to you in a percentage. So when you see those percentage values of R and R squared in your calculations, what you're seeing is that when first the R value, when this is occurring, this percentage of time, this other thing occurs. That's the R value. And then the R squared, that the percentage of this outcome is being caused by this input. Okay, so the percentage of Y, the dependent variable, or sometimes it's called the predictor variable. Excuse me, the response. Yeah, the predictor variable is sorry, I don't want to confuse you. Okay, the predictor variable X, the response variable Y. Okay, so R squared is telling you the percentage of the response variable, that is the Y, is being caused by the predictor variable, or the percentage of the dependent variable Y that is being caused by the independent variable X. Okay, so remember those two. Very, very useful if you're trying to make a determination of, let's say, how do people behave when you have certain voting hours, or how do they respond to a message? And you can create surveys in which you numerically code those responses. So for instance, one of the common applications of regression analysis in political science, somebody gives a speech. All right. And then you have respondents listening to the speech. Maybe even you have a test group. So you bring groups of people through a room in batches of 20. All right. Sort of the Frank Luntz method. Okay. Then you have them watch a speech. And then you have them take a survey saying, when you give them a scale 1 to 5, number 1 is strongly disagree. Number 5 is strongly agree. Number 2 is disagree. Number 3 is no opinion. Number 4 is agree. So you give them a numerical scale to express their emotion. So the speech is given and you say, please take this survey and tell me what you think. Okay. And they say, and you ask them questions like, I feel the candidate spoke directly to me. Strongly disagree, strongly agree, right in the middle, no opinion. I feel the candidate is well informed. I feel the candidate has my best interest at heart, or whatever your survey questions are. Then you get those numbers. Okay. And then you can make, say, your independent variable, the number of times the candidate says taxes, because a speech is just not like a candidate going, oh, what am I going to talk about? It's been carefully written. So then you take the number of times that the word taxes are said, that becomes your X. Put that into the calculator. And then you put the numerical responses from, say, people who strongly agree that they feel like the candidate understands them. You put those numbers into the dependent variable, the Y, and you push the button on the regression calculator, and you'll get a numerical expression that tells you, number one, the R factor, the percentage of when people think the candidate is speaking to them at the same time that the candidate is talking about taxes is whatever R is. And then the percentage of time that people think the candidate is speaking to them that's being caused by the candidate talking about taxes. That's R squared. So this becomes a tremendously useful tool in empirical research. Okay. All right. Question number 2. I asked you to tell me what do the R and R squared values that you found for both regressions suggest about the relationship between comorbidity and severe COVID outcomes. So remember, this data, this is a collection of 101.4 million COVID cases tracking their severe outcome and the types of comorbidities that is existing diseases those who got infected had. Now, here's a little caution. I want you to remember this too about R and R squared. The values of R and R squared are only as good as the data that goes in. So if if there were cases of severe outcome that were driven by comorbidity that weren't recorded in the data set, that's going to affect the R squared. If there were cases of severe outcome that were recorded and attributed to comorbidities and COVID, that will affect the R squared. So before you start grabbing data and shoving it into a linear regression calculator, check to see what the data is. Check to see where it came from, how it was gathered. Check to see if there's any irregularities in it. You might get a few things here and there, but if it's any significant number, it's going to affect the output, right? So be cautious of that. But in this case, I've already looked at this study and I looked at their methodology, and the data look pretty clean. Okay, so let's go to question number 2. What do R and R squared signify? Again, I'm going to go to you, Ashley. Regression measures how one variable affects another, and the R and R squared values are important components. Actually, I'm sorry. I think I'm reading the same one again. Okay. So, Ashley, you picked ages 0 to 17 and then ages 60 to 69, quite a spread. Okay. And you picked, 2 or more comorbidities versus, I think I asked you to pick 0 more comorbidities, and I think you only picked. Okay. Okay. I'm sorry, Ashley. Okay. All right. Well, let's take a look at the comorbidities that, the R and R squared for the 2 comorbidities. Okay. So for ages 0 to 17, the R value is 0.956. So if you times it by 100, that's 95% of the severe outcome is driven by the comorbidity, or they occur together. The R squared is 0.9139, times it by 100, that's 91.3%. So 91.3% of the severe outcome is driven by the comorbidity. Okay, and then here's what you write. Based on the above values, we can conclude that there's a strong correlation between comorbidities and severe outcomes. So they happen together. Okay, in this case, percentage rates of acceptance to hospital. According to this data, there's also a greater likelihood that age increased the risk of admission to the hospital in addition to presence of existing conditions. True, but there's also something else here that I want you guys to pay attention to. Regardless of the age group, if you run this data, the causal relationship of comorbidities and severe outcome is really high, like in the 90 percentile. Okay, and as I tell you in the beginning of the sheet, the instructional sheet, coronaviruses have been around for a long time. They're not going to go anywhere. They're actually a very common respiratory virus. The reason they got their name, now viruses are extremely small, and you can't see them with a naked eye or a magnifying glass or a regular microscope. Why? This is an interesting explanation, something you should know. Okay, the only way, I'm fishing around for some props here. The only way that you can see something is if you can bounce a photon of light of that thing, bounce a photon of light off of that thing, and then that photon enters into your eye and registers in your eye. Okay, so let's say here's this rock. Okay, this is a piece of volcanic rock from East Africa, from Mount Kilimanjaro. Okay, when I hiked up it, I know you're not supposed to take the stuff, but okay. So the reason you can see this rock is that, and imagine this penny right here is a photon of light, or is that photons are bouncing off of this rock and coming into my eye. Okay, but what if the thing that you're trying to look at is smaller than the photon of light? And that's where viruses are. They are very, very small. And if the thing that you're trying to bounce off is bigger than the thing, then it's not going to bounce off, at least not going to bounce off in a predictable direction. So it would be the other way around. Imagine this is the virus and this is the photon of light. This thing is not going to bounce back, and you're going to be able to see it through a microscope or with your eye. So how do you see a virus? You have to find something even smaller than a photon of light to bounce off of it and then come back. And we can use beams of electrons. Electrons are what move through along a wire, and that's electrical current. And when we bounce those electrons off, and we cannot see straight electrons, but we bounce them off, and then when they bounce off, they bounce onto a sensor that registers those electrons and then turns that input into a picture that we can see. Okay. So coronaviruses get their name because they look like, when you see them under an electron microscope, they look like, have you ever seen pictures of like a total eclipse where the sun moves into the shadow of the moon, and then you get like this flamey edge all around? It's like black. That's what a coronavirus looks like under an electron microscope. It looks like the corona of a solar eclipse. That's where it gets its name. Okay. Sorry, long detour for a short explanation. Okay. So coronaviruses aren't going anywhere. Been around for a long, long time. Okay. We get them and they come and they go, and we build up immunities, and then they change and they come back. Okay. So the question is, how do you not have a really, really nasty outcome once you get them? Okay. So what I wanted you to do is screen capture question number 3. Both screen capture and post both scatter plots and R values for your simple linear regression. Okay. So what I want you to do is run a linear regression between, the various ages for no comorbidities, one comorbidity, and 2 comorbidities. And I want you to look at the lines. Okay. Now, scatter plots do not come with lines. The lines are drawn in for you. And what you do, because you'll often, with a scatter plot, you get a lot of data points, and you try to find about what would be midway. You try to look for a pathway, sort of squint your eyes and look for a pathway through these dots, where are they sort of coalescing? And if they're all over the place, this is a dead giveaway to you that there's not correlation and there's not causation. Linear, that's where this gets its name from, the line. We're looking for the directional line. Okay, so let's just start taking a look at this. So let's look at yours, Susan. This is question number 3. Okay, so let's look at the age. We'll start with the one on the bottom, Susan. Ages 0 to 17. You guys, I don't know why interesting ages that you picked. Anyhow, okay, so If you are 17 years of age or younger and you got COVID and you had no comorbidity, all right, so zero comorbidity, your chance of being entered into the ICU, because that's what Susan looked at, were like nearly 0%. Because the bottom of the scale is -5, and you can't have a negative, percent of being entered into the ICU. Okay, so it's like virtually none. All right. If you had one comorbidity, now your percentage, the chances, being driven by you getting entered into the ICU goes up to about 3.5%. It looks like here from the graph. If you have two or more comorbidities, yowie kazowie, it jumps up to nearly 20%. Okay, that's a really high causation, really high. Or look at the top one, 80 plus. R value is 0.94, so 94% correlation, 90%, causation, that's the R squared. So if you're over 80 and you get COVID, no comorbidities, your chances of being sent to the ICU are really low, like 1%. One comorbidity, they jump up to, looks like about 57%. Two comorbidities, they jump up to 70%. Okay, that's how you should read these documents. Now I'm looking at Stephanie, and I think you want to redo. I don't think you did your hospital rate correct, because you have you got to be careful of your numbers here, Stephanie. I think you've done something wrong. All right, because you have, for your zero comorbidity, a hospitalization rate of 40%, your one comorbidity, a hospitalization rate of 20%. All right. So, in other words, you've entered something wrong, because we know from the data and from everybody else's stuff that the causation of hospitalization rate goes up, not down, with no comorbidity. So check your math again. Okay. And I think some of you people in the class are saying, hey, there looking like there's a problem here. Yeah, Susan, I think you're talking about that. Okay. All right. Do you understand how to read these graphs? Now, if you don't, reach out, talk to me. We'll spend some time with them, and you'll get it. Okay. Question number 4. Recall your experience of 2010 to 2021 COVID pandemic. You recall media emphasis on the causal relationship. Causal, remember, not correlation, between severe COVID-19 outcomes and comorbidity. Why, in your opinion, did the media cover or not cover this causal relationship? Excuse me. All right, Susan, you went first. We'll take you first. I remember during COVID having much skepticism as a young high schooler who was annoyed that their senior year being taken and not believing in the severity of COVID for everyday person. I personally had a friend who had been battling cancer at the time and contracted COVID and passed while in the ICU. That would be a comorbidity, cancer. Her death cause was noted as COVID rather than stage 4 cancer she'd been battling for 5 years. Interesting point. This is one example of comorbidity not being taken into consideration. I think that unfortunately there are many other cases such as hers in an attempt to scare people into voting the way that various parties wanted them to. Now, this is why I gave you this study, by the way, okay? And I'm not taking partisan sides here. I mean, I have my opinion, and you can look me up in the press because I've written about it a lot, but that's not what we're up to. Remember, we're to be investigators, not advocators, when we have our research hat on, okay? All right? But you had to be living in a cave not to have gotten and had some awareness or understanding that COVID became a tremendously political and politicized issue. From the money allocated to give out free vaccines, to closing schools, to mail-in ballots, all downstream, tremendously political. Okay, probably one of the more significant politicized events thus far of your lifetime. There may be others. I don't know what's going to happen in the future, but that's why I picked this one. Back to you, Susan. The number of COVID deaths was a large fear-mongering tactic used in 2020 election and the months to follow. This lack of information around comorbidities surrounding COVID deaths was to keep people at home. The world was shutting down for whatever reason, and they wanted people to stay at home and not get sick. In order to do this, the number of COVID deaths needed to be inflated as possible, meaning at the time many people who passed away from COVID were counted into the statistics of COVID death without other outside influences being considered. And that is an excellent statistical, empirical point. Because if you look at the data and you take out the comorbidities, the chance for severe outcome, starting with even just showing up to the hospital, goes down for most age brackets, especially say if you're under the age of 50, goes down to like 0. Now, remember too, when you're doing in empirical research, when you're doing quantitative research, okay, that there is the 98, 95, 65 rule. Okay, that is, there's always a percentage. This, you'll see this in surveys. They'll say, plus or minus 3%. Plus or minus 3% means this has a 94% confidence interval, meaning that they expected basically nothing to happen 94% of the time. But there's this, plus or minus 3%, of which, we don't know what's going on. Okay. So if the hospitalization rate falls below that 6%, let's say 95% confidence interval, there's no causation here. And if you look at the data and you take out comorbidities and then you look at severe outcome for groups all across the board, for say 50 and healthy and under, the severe outcome rate is less than 3%, which is less than your percentage chance of being in a serious accident with a severe outcome, meaning severe injury or death. So in other words, if you did not have a comorbidity and you contracted COVID, your chances of anything really bad happening to you were lower than the chances of something bad happening to you that you incur every time you put yourself in a car. I guess we don't use keys anymore, Every time you push, and maybe some of you do, we push the ignition button on our car. Okay. So this part of the reporting and the politics of this event. Okay, back to Susan. Without other side influences considered, how would this have affected our society differently without this media influence and statistical inflation? Will not ever be certain. The conclusion is that yes, COVID was very dangerous for my friend with stage 4 cancer and likely increased her chance of dying from it. But myself, a healthy 18-year-old at the time, may have not, we can say causally, Susan, did not need to worry as much as was indicated by the major media storm. And that's exactly it. Okay. And again, I'm not taking political sides here. I'm not saying what party did this, whether it's Rand Paul or Anthony Fauci or that. Look at the numbers. This is the gift. This is the benefit. This is the reason for empirical research. It's because you can cut through the motivations and just get down to the numbers. Okay. All right, everybody. Try to keep these at 30 minutes and less. So know what R and R square and the difference between causation and correlation. And yeah, we might have some questions on politicization of events and how this was used. So make sure you watch this carefully. Okay. And if I'm going too slow for you, put it on double speed or something. And get through this in half the time. All right, everybody. Have a wonderful, wonderful week. I think about you. I pray about you. And I will see you next week. God bless. Bye-bye.